Okay, ladies and gentlemen, let's come to order. Warm-up today was a refreshing reprieve from an optimization problem, right? Nice, easy warm-up. So you'll see why I did something so simple for our warm-up today in a minute. Here, you'll see what we're doing today. You'll like what we're doing today. We'll give you a little bit of a reprieve before we hit you again. It's a little bit hard with related rates. So gotta give you a little break in here. That being said, let me at least address the setup on one of the homework problems here. By the way, this is kind of a classic optimization problem that maybe you've even encountered in a pre-calculus course. Obviously, any optimization problem we've been doing, you could have encountered in a pre-calculus course. In fact, like the viewing angle thing, I think actually I do have that as a homework problem in my pre-calculus course. It's just in pre-calculus you have to just find the maximum using your calculator or something, or find the minimum or something, right? So anyway, so this is actually a problem of similar nature, at least, that I give in my Algebra 2 classes. It's like we've spent a whole day working through this problem. And, anyway, so there's a little discussion here. The key relationships you need to understand are these. I kind of wrote them off to the side in order to kind of set this up properly. You need to like interpret distances and times. You got to like figure out what's going on there, right? So this diagram I think helps if that's not. It is actually a good question. Like, how do we, there must be an optimal point next time you like are boating, or the problem I do in my Algebra 2 class is like walking through the sand and then along the road, and it's slower to walk in the sand than on the road. But there are lots of cases in life where this kind of comes up. You might be thinking, no, there aren't. Well, I'll give you one example. From this, you can derive something called Snell's law. And because either both light and also sound waves travel along an optimal path, and so why do they choose to bend at a certain point? Well, it's because the two mediums, they travel at different speeds through different mediums. So I challenge you just in general to derive Snell's law from this idea, right? It falls out right nicely. You've seen that, but even if you've never studied physics or anything, you know that light bends as it goes through water. Well, why does it do that? I mean, you could use calculus to explain that, for example. In fact, calculus can be used to explain basically everything. So I guess it's not even worth mentioning, maybe. Okay. Here's the second half of that problem. The first half is the most important thing, though, right? How'd you get that set up? I can show it to you again if you need to, but I just thought that's a really kind of an interesting problem, and I'm sure some of you struggled on that right off the bat. And you're like, oh boy, this homework's going to be a mess. But that was a little bit of a harder problem. The other ones were not quite as bad as that, right? For the most part. Some of them they're all a little dicey. But good. I mean, like I've said before, you're in the gym here, right? Some of these are have some heavy lifting problems to do. They're not. They take a little while to get into. So any other comments about this, or I mean, we have a lesson to get to here, but I saw some people struggle with the trapezoidal trough kind of problem, gutter, or whatever it is. That's a nice one. Again, geometric visual thinking here is kind of winning the day here. If you're like a strong spatial visual person, then I think you do better at these maybe. To provide some good practice in geometric thinking. So the solutions will also be posted online, but make sure I do get my 3 hard copy sheets that are being passed around. That I get those back eventually. Feel free to look at them or take a picture of them or whatever you want to do. So, but just make sure I get them back. Those are Mr. Chase originals, Yeah. Limited edition. Yeah. Someday when I retire, I'm going to sell these on eBay. You'll see. Okay. So today we're going to talk about something, like I said, that hopefully will provide like a little bit of respite. I think you'll find this to be not quite as challenging as what we've been doing. In fact, we've got a big fancy word for something that, in fact, you already know how to do. We're going to talk about it in maybe some different terms, just a little bit. But really, it's something that you've already been doing all along, like you did in the warm-up today. And that's just like finding the tangent line to a curve. But this is kind of a big, powerful idea that we want to like talk about as maybe a bona fide application of the derivative stuff that we've been talking about. So this like idea of local linearity, we've talked about it that way before. This habit of mathematicians and physicists to like just assume complicated behaviors are locally linear let's just pretend it's a line, is like a huge idea in calculus. So I have some things to mark on this diagram just to put some language on the table. So we've got some tangent line at x equals a. We've got a point f of a, and we call the equation line that we came up with in the warm-up today, for example, we call that the linearization of the function. So new word for something that you already know. So okay, new word for something, that's all I'm introducing. It's a new word, linearization. Notice again, like, boy, that blue line really does look exactly like the curve if I'm like here. You know, you can't even tell the difference between them. For some small distance from the tangent point is, of course, the key, though, right? You okay? Sorry, Bavesh, or whoever else needed. Okay. Yeah. Really, the only new thing on that slide is the word linearization, so I just want to underscore that. Wait a while, there's no meaning in this. Okay, so how do we come up with the linearization of x at a in general? Well, I think you already know, but let's write it out. For x equals a, we have f of a and f prime of a. So what would the linearization be? This function, what would be, the way you wrote it in the warm-up was y minus, in this language, y minus f of a equals f prime of a, let's use this language, times x minus a. Do you agree? I mean, that's just in general what we would write. In fact, because we want to maybe think of this as a function, I might also move f of a over to the right side. So doing that gives this form, but again, it's in a box, but I hesitate to put it in a box because it's really, I promise, just the thing we've been talking about all along, isn't it? It's really just point slope form. I hope you can still see it. But I want you to still see it. I want you to see it in a slightly different light today. And we'll highlight the different pieces of it as we go. But for now, just recognize that it's something you already know. So we would call this the tangent line approximation or the linearization at x equals a. Especially later in the year, we're going to call this the first order approximation, hinting that there might be more here too that would give like a second, that there might be such a thing as a second order approximation of a function or a third order approximation of a function. But if you were looking for a first order different approximation of the function, then this is it. And for, like we've said before, f of x is close to L of x for values close to a. We can use calculus to make that statement more rigorous, actually, right? The idea of limits. So now we have three names. I've introduced three names for the same thing. That's good. Must be an important idea. So three names.
Why is it an approximation?
I mean, so L of x is the tangent line approximation, right? It's the tangent line.
Yeah.
So what we're saying is that actually, pretending that the original function f, which might be some crazy curve, pretending that that function is just this line, this linear function L of x, is actually not too gross of a mistake if you're somewhat near a. If you're at a, it's not a mistake at all, actually. Right? If you're near a, it's actually not a bad assumption to just assume it's this line. But they're not the same, though, just to be clear. L of x and f of x are different things, right? So here's the warm-up example. So found that the linearization was 1/2 x plus 1, didn't we? L of x, we could call it. So just to illustrate this idea of how close it is, I'd like to actually kind of like run some numbers on this. Just, I know this all came up at once and it looks a little intimidating. But I'd like to actually compute the value of f and the value of L at various values here. And then this over here is just comparing the difference between the two. Now, the first one's not too bad. What's f of 0 and what is L of 0? Now, why should they agree and why should the error be 0 there? And is this like, oh wow, that's a very special example, or does this always happen? Why would it always happen? I mean, what do we do? What is the linearization? How do we derive it? What property should it have that should make this kind of obvious that it'll always be like 0 here, or the same value there? Yeah.
Since the value we used was 0 to make the L of x, then of course L of x and f of x will be equivalent to L of x.
Yeah, I mean, right. In fact, we could write it out again here. What is L of x? It's equal to, oh yeah, that's right, f of a plus f prime of a times x minus a. And if you plug in a, that is the center where you put it, you know, the center of your tangent line. If you put in a, what do you get? Right? You just get f of a. So of course, just the way we set this up from the very beginning, if we're at a, then of course they agree. That's the place of tangency. Of course they agree. That will always happen. Okay. This should make sense. All right, but what about if we're really close to 0? Should be true that maybe we're still close, just intuitively. But let's actually calculate for these how close we are. I might actually pull up my calculator for this, and you can put this in y1 and this in y2, and then, you know, use the ask feature on your calculator, type these in, or however you like. Where's my calculator? Sorry, I know I'm blocking the view for a second here. So I'm going to put the first one in y1. And I actually want to compare these two. We've made a claim that these are similar, but let's see if we can quantify that. Oops. And by the way, like I said, some of you were wondering how you do this ask thing. Have you done this before on your table setup? You can do ask. Don't care about that, actually. Where's my table? Table, there we go. All right, so we can actually maybe type this in here. What is it? So 0, we got 1, 1. Actually, I plugged in over here. I put in y3. I made that y1 minus y2. I don't know if you saw me put that in, but that's not a surprise. So 0.05, pretty close. We can actually, again, compute how close they are on the order of, 10 to the -4th power, right? So very close still. It's a very suitable approximation for a value like 0.05. Definitely suitable for 0.005. Let's compare. The answers on your calculator even appear to be the same, don't they? At 1, that's a little further away, but still, it's not terrible. We're still only 0.08 off. And at 2, we're suddenly not very good anymore. By the way, I'd actually kind of be curious to graph the error function, right? This is going to be interesting to me. Actually, I don't even care about the original two functions. I got the tangent line and I got the square root function on there. Let's see, what should that look like? Now, it's only defined for values where the square root function I have is defined, so for values like greater than -1. But what should it look like? If we start graphing these values over here that we're getting. Yeah, hopefully it gets bigger as it goes out, right? Let's see what it looks like. I guess I'm fine with whatever here. Yeah, whatever. Zoom standard, whatever it is. So the error is 0 right here. And this, I have f minus L, so I think that's that. What does that mean for us? Is it always? Seems like this is always below. It's always negative. Why is that? Yeah, the line always overestimates the curve, which does say says something about the concavity of the curve too, doesn't it? Like if the linearization always overestimates the curve, then the curve must be concave down. Would be one way to say it. I don't know if we. Not necessarily concave down everywhere, but certainly concave down at that point. You know, maybe it goes up and down later. We don't know. But here are some linearizations just for fun. The one we just did is this one right here with k equal 1/2. And actually, interestingly, if we had, instead of 1 plus x to the 1/2, which is what we were just working with, if we had other things, we get actually the same linearization. And except with a different k value there. Other linearizations that are important that will come up are these here. This is meant to be x. This is not right. Mistake in the PowerPoint. There you go. That's an x. So sine x, is that believable even without actually running the numbers and doing the tangent line approximation for sine x near 0? Is it believably just y equals x? I think so. And if I haven't already mentioned this before, that's sometimes called the small angle approximation for sine. A lot of times if you're dealing with a very small angle, like what do you think the sine of 0.01 is? The answer is approximately 0.01. Right? That's what that's saying to us. It's kind of a powerful idea. In fact, it's one that, again, physics people use all the time when they're dealing with like rotating bodies and pendulums and stuff. Let's just assume that the sine of the angle is the angle, right? It's not a bad assumption for small angles. So. Tan x is also x2. Again, convince yourself from the picture or actually work it out yourself. Yeah. So, and of course, this is not an exhaustive. Yeah, this is not an exhaustive list. Obviously, you could come up with other approximations that are interesting to us. But I thought these were interesting. I think these are your book highlights too, maybe. So that's why I put them in there. But this is interesting, by the way, too. If the k happens to be not 1/2, if it's say 5, then what do you do in order? Like, what would you have to do if you expanded this out? Actually, if it was like 1 plus x to the 5th, and you expanded it out, why would this make sense then? What happens when you expand this out if you do 1 plus x to the 5th? How does that expansion at least begin to look? Yeah.
It goes like way up, right?
Well, what are the first couple terms in 1 plus x to the 5th? Let's write a couple terms out. The first term is going to be 1. You know, the binomial theorem would tell you all of them. But let's just do the first 2 terms. How many terms have an x on them? How many terms have an x on them? No, I mean, if you actually look at all the brackets here, how many is that? Oh, yeah, aren't there 5 ways to get an x, right? And then there's some other stuff, right? Including at the very end an x to the 5th. But I think I see the linearization just sitting there, actually, right? Right, in the expansion, if you were to expand it out. Now, you might be thinking, how do I expand? Does the binomial theorem work? If that's like a 1/2? Surprisingly, the answer is yes. We just never studied that in pre-calculus. So you just get an infinite series. You don't get a finite series. So anyway, whatever. Here's an interesting problem. This is less interesting maybe now we have like calculators to help us with this. But can we get a decent approximation for root 80? And let's center our linearization. There doesn't seem like to be a function, this chase. Well, let's maybe think of the function being, I don't know, f of x equals root x. And then at what center seems appropriate to you? And by an appropriate center, here I'll use a, I guess, as use the same language we've been using. This is a struggle here. Okay. what would an appropriate center be? Maybe not 80. What I'd like to be able to do is I'd like to be able to evaluate the function at this center. So, and we want a nearby center. I've tried to make it somewhat clear. Yeah, what's it going to be? Yeah, maybe 81. Because I know the square root of it, that's why I'm choosing it. Okay? So I think that would be a good center for my linearization. So let's actually write the linearization of this. We're going to need the derivative. That's cool. We know how to take the derivative of that thing. So what is the linearization going to be? Let's actually write it out. And then we'll actually figure out why that's useful in the problem in a second here. It's going to be f of 81 plus f prime of 81 times x minus 81, right? Isn't that the tangent line approximation? What is f of 81? Let's see what I'm saying. We actually know that, don't we? That's why we're the great A to choose. If f is just root x, then what is this? Our linearization, we can write it better here. It's equal to 9 plus, and actually we can figure out what f prime of 81 is too, can't we? What's 81 to the negative 1/2? That'd be 1 over 9 times 1/2. So 1/18 times x minus 81. So, all right, so here's our linearization. That is, I'm not going to put a box around that, but that is beautiful. That's nice. And what is this good for? Well, it's great for approximating this function, f of x equals root x, near a. Isn't that a great use for this function? Isn't that what we said the linearization could do for us? So, you plug in 81, for example, you get 9, don't you? Let's just be clear about that. It's not really an approximation there. We kind of set it up. We set ourselves up for success on that. If you plug in other nearby values, though, you get decent approximations for those square roots, don't you? So, like 80, for example. If you plug in 80, f of 80, the square root of 80 is approximate is equal to f of. And we can actually say what that is approximately, right? So we're going to approximate the square root of 80, which is really just f of 80, which we say is approximated by this function, L of 80, the linearization, the tangent line. So it's kind of nice here, right? In fact, can you see why it's not just like a lazy man's move to leave our linearizations in the point slope form? You might have been thinking like, well, okay, like I see why we do that because we're often in a situation where we have a point and a slope, so it's easiest to use point slope form. But really, most people really want it in slope intercept form, don't they? The answer is no. Actually, this actually turns out to be a very, very useful form in many, many cases. Like here, I'd actually rather leave it this way. Please don't multiply this out. So, because now when I plug in 80, it's a huge convenience to me, right? Done. Yeah, right. So I don't know whatever that is. 9 plus 118. 8 and here we'll write it as a mixed number, just because we're 8 and 17/18ths. Or you can write that as an improper fraction if you like to. But it's just an 18th short of that. Do compare this with the actual square root on your calculator, or at least the approximated square root. Can we just check and see how close we are? I'd be interested to know. Again, this is an approximation for the square root of 80. It's not the square root of 80. But check how good it is. See how it's not bad?
Yeah, it's pretty good.
How far off are we?
We're 0.06.
It's close. All right. It's within a tenth, within close, yeah, 200ths away. Didn't you say 0.02 off?
I said 0.003.
Oh. Really good. So far, so good? Okay, we good on that? All right, one more important idea is the following idea of a differential, and it's a thing we've already been using, but we haven't really ever separated these and thought about them as different things, dy and dx. We're about to do that. Okay. So we even go back to the very beginning, so when we first introduced dy and dx, and we talked about that really being kind of like a very small change in y or a very small change in x. So I'll use kind of delta, I'll use the delta x and the dx kind of interchangeably in next set of slides here. So far, do you agree with what I have here? I have a and a plus a little change, and those result in, of course, a and f of a plus delta x. So looks like we're kind of almost set up to do the derivative or something. And that's, of course, that difference over there is the change in y. And the change in y over the change in x would just give, that average rate of change on that interval, if you like to do that. The thing I want to focus on here is this other function in blue, the line. And, of course, it gives a different value up top. Does it give a different value down below? No. F of a and L of a are the same thing, aren't they? But f of a plus delta x and L of a plus delta x are not quite the same, but they're pretty close, right? They're pretty close for values, again, close to a of x. So I think this picture is helpful. We'll show you one. And again, if I didn't say already, there it is again. We're going to use, like I said, use delta x and delta and dx interchangeably here to some extent. Why not all came up like one of the same? But we'll go with it. Go back for a second. Okay. So keeping in mind our actual definition of what we mean by the linearization, again, just let's never lose sight of the fact that that's just the tangent line. Okay. What is if dy is approximately delta L, that is that change, if the change in y is close to the change in L on that last slide, did you see that? And they are, right? Again, if we're close to the point of tangency. But these shouldn't be too far off. That's kind of the point we've been making all day. Then what is delta L again? Let me just make sure this makes sense to me. Delta L is the change in L, right? And that was L of a plus dx, that's this value over here, minus L of a. Isn't that the two things that were on the side? Isn't that the delta L? Go back to the previous slide for a second, just for a second here. I'm asking, what is delta L? Isn't that the change in L over this interval? How much L changes? Well, L has this value, L of a plus delta x. And here, at the bottom here, it has the value L of a, which is also known as f of a, right? I'm just going to make that replacement there. Okay? So you could have minus L of a, or you could have minus f of a. They're the same thing. And then again, keeping in mind what we mean by L of x isn't by L of a plus dx. If you plug this in to this function, don't you get this in blue? I'm just replacing blue with blue. All I did is replace the x in this equation by a plus dx. All I did in this equation is replace the x by a plus dx. Do you agree that that's what this is asking you to do, L of a plus dx? And of course, so I just copied that down with, instead of an x, an a plus dx. And when I do that, I get an f of a out front here that cancels out with the f of a back here. And in here, of course, I just have an f prime of a times a dx. Now, this is a long way around to get to this, but this should make sense, too. Well, how do we approximate the change in y? Well, what's f prime of a? Well, that's the derivative at a. That's the change in y and over the change in x at a times dx, so some small change in x. But of course, that makes sense pretty clearly that this would be our definition for the differential dy. Because this says, because there is another way to say this, right? Yeah, if you divide both sides, but I just want to, because before, if we divide both sides by dx, then of course you get the thing that doesn't surprise you at all, right? You're like, why did we go through all that? Right? Well, the answer is that before we go just like taking this equation and multiplying both sides by dx and being like, oh, well, then this follows. I need to like lay some groundwork here, because this is to me still just kind of like a mysterious symbol, right? Like we've never actually separated this before. So I would kind of the reason I like this way of thinking about it right here in the box is because what this says is this kind of gives a input and output response kind of feel, right? If you vary your input by just a little bit, how much does the output change? Is what this is kind of communicating, right? If you just have a really small change in X, how does Y respond to that? And I can think of a lot of real world contexts where I care about this. The first would be like actual error analysis, right? Like how bad could it be if I'm making this rocket and like my measurements are off by only a millimeter? You know, whatever, you know, it's not a big deal. Well, how does that affect if I've got a millimeter wider radius than I meant to on something? How does that affect the area? Is it also a millimeter off? Not necessarily, right? Depends on how the area depends on the radius in this case, or whatever else, right? You can think about this with a ton of like response variables in life. How does some outputted value respond to variations in the input? Is a huge question that doesn't just deal with errors. Lots of other continuous functions, right? Is that good there? So we've actually, and if you didn't notice, we actually defined what we mean by the differential dy here for the first time. We've never actually like come out and really said that per se. But now we can maybe say that here. Yeah, we can use them separately. This is an interesting idea. All right, so this is exactly that. Like, so what happens if if we're 0.1 away on this function? How do the outputted values respond around t equals 2? Right? That is, what is dp? I guess we're calling this p, sorry. P prime of 2 times dt, right, which is 0.1. Isn't that what we said in the last slide? Isn't the change in y, dy, isn't that equal to p prime of 2, or the derivative of this function, evaluated at the center where we're looking at, center nearby there, times the change in this case, t. I know this seems a little weird to like say dt equals 0.1. It'd be fine to like say delta t too for our purposes. We're being a little flexible between those two notations. But this is approximately given by this, right? What is p prime of 2? I haven't figured that out yet. I need to figure that out. So I'll do that off to the side here. What do we get? Is that 25? No, sorry. 10. 12 minus 2. Well, that makes this easy, doesn't it? I think I know what that one is. Okay, so dp is 1. We'll say that. But actually, if you actually compute the difference, if you actually plug in 2 to this function and 2.1, of course you'll get something a little different than this, won't you? Because we used the linearization, didn't we? We used like this idea that we pretended that it's linear, right? So it's not bad. If you actually compute p of 2 and p of 2.1 and see what the difference is, I think you'll see that it's about 1. But that tells us a lot, doesn't it? You see what that's saying? That says like, oh, if we're only off by 0.1, it's not going to make a big deal in the outputted value of y. Yeah, actually it is. It's going to be like 100-fold that, right? I'm sorry, it'll be 10 times that, right? If you had 0.1 and the response is a difference by 1, that's like 10 times off, right? Than what you're in. You're going to get values that are about 10 times different, aren't they? do this with a circle here too. I don't have much to say about this, right? This is kind of like what I was referring to either, right? I think you know the area formula, so I'll let you write it down. On this one, maybe we'll actually compute the actual change in the area too. Do both. Maybe we'll do both. I think you'll like this one. So A of R, I guess we'll think of this as a function. A of R is pi r squared, of course. And if the radius is 10, then we're talking about 100 pi is the area. Well, I guess we need A prime of R2. That's 2 pi r. Okay. So what is the change in area? Let's call it dA. Well, it's A prime of R times dr. But what's A prime of R? It's 2 pi r. We have a dr there too, right? That's interesting to me, right? Again, in fact, this provides, let me make sure we were clear on why this is such an interesting equation to look at. This tells me that if I change the radius by a little bit, the area changes by a factor of 2 pi r times that, which is the circumference, right? Which kind of makes sense, right? As we're changing, what is that? What is that strip along the edge that as we change the area of the circle? Well, it's the circumference, right? This happens to also work for other areas and volumes too. We'll see. Good. So now we actually have to do the answer to the question too, right? So 2 pi times 10 times, what are we doing? 0.1 again? I love 0.1. Okay, that's good. So it just comes out to be 2 pi. That's the answer to the question that was asked. But I would just like to calculate what is A of 10.1 as well. It's going to be 10.1 squared times pi, whatever that is. And can you just do the subtraction here? What's A of, I'm just curious what the actual difference is and see if it's anywhere near 6.28. Someone tell me what that is. Is it close to 6.28? 6.31, yeah. Not too bad. Like I said, homework 8 tonight will be doing lines and stuff, and we'll welcome reprieve from boats and troughs and all that kind of stuff.